All right, so moving on to the atomic structure of magnets. Okay, so we need to think about a single atom. So inside every atom, there are moving charge particles. You could think about them as little subatomic currents. So we have moving electrons and moving protons, actually, for that matter. So, and these produce tiny magnetic fields. I mean, those electrons are just whipping around, going in and out of their quantized locations. And in magnetic materials, these dipoles magnetic moments add up to a non-zero total magnetic moment. All right, so there are three sources of currents. You could have an electron orbiting a nucleus. You could have an electron spinning on axis. And you could have rotational motion in the nucleus. Because remember, protons and neutrons, well, they have spin too. Now, if something has spin, so it's moving around, so the electrons, they're orbiting around its axis and they're orbiting around a nucleus, then they all have angular momentum, which remember, angular momentum has to do with circular motion. So all these particles have angular momentum. L. And the magnetic moment is related to L of the particle. And we're going to look at this relationship and derive it. So mu is equal to some factor that we're going to work on times L. All right, so we're going to use some really simplistic models, which we're going to see they're going to be good enough. We're going to use actually the Bohr model of the atom, because if we were to think about these quantized electron clouds of a wave, that's really hard to model in our heads, but we could think of an electron spinning around an axis. That is way more doable. So we've got an electron going around in a circle, and it's orbiting to the left. All right, so now we have a current loop. For a current loop, we have our positive charge, we've got our radius, got our little minus E, so U mu is equal to I times pi r squared. We're just going to treat this like it's a little loop. And we want I for 1 electron. All right, so we need to get orbital time. So orbital time, and we get this from thinking back to angular momentum, period t is equal to 2 pi r v, and we can say I is equal to E over 2 pi r v, which is equal to EV 2 pi r. And so the magnetic dipole moment of a single electron mu is equal to I pi r squared is equal to E v 2 pi r squared. Mu is equal to 1/2 E r v. Now, we need to relate this to angular momentum. So if you recall, L in circular orbits is r cross p. And in the case where you've got r perpendicular to p, so in other words, we've got a perfect circle, then L is equal to rp sine 90, which reduces to rmv. And this is, of course, for v much, much less than c. So mu is equal to, we're going to add in a clever 1, m over m, 1/2 ERV. And so from here we get this is equal to 1/2 E over m RMV is equal to 1/2 EM over, or E over m times L. So that was, our whole point was to get something where we would have angular momentum right there. These are the games we play. So now we have our factor. Our factor is 1/2 E over m. So for an electron, 1/2 E over m is equal to 1/2 1.6 times 10 to the minus 19 coulombs over 9 times 10 to the minus 31 kilograms, 8.9 times 10 to the 10 coulombs per kilogram. And for a nucleon, 1/2 E over m is equal to 1/2 1.6 times 10 to the minus 10 coulombs over 1.7 times 10 to the minus 27 kilograms, which is 4.7 times 10 to the 7 coulombs per kilogram. And so what we can see from here is that magnetic dipole moments come from electron orbits, which are quantized, as we learned about in Chapter 8. And so that actually implies that angular momentum is quantized. So the angular momentum, NH bar, for this, then N would be those quantum states, 0, 1, 2, 3, etc. H bar, 1.05 times 10 to the minus 34 joule seconds. So for N equals 1, L equals H bar. So mu is equal to 1/2 E over m times h bar. Mu is equal to 1/2 times 1.6 times 10 to the minus 19 coulombs over 9 times 10 to the minus 31 kilograms times 1.05 times 10 to the minus 34 joule seconds. Mu is equal to 1 times 10 to the minus 23 amp meters squared per atom. So let's look at our example. So the bar magnet we looked at had a mass of 56.4 grams, and we're going to assume 100% of the atoms are iron, and the mass of 1 mole of iron is 56 grams. So the number of atoms, little current loops, is 56.4 grams over 56 grams per mole times 6.02 times 10 to the 23 atoms per mole. N is equal to 6.063 times 10 to the 23 atoms. And of course, what we're after is the magnetic dipole moment. Mu is equal to N mu of an atom. And we've derived mu of an atom, so we have 6.063 times 10 to the 23 little current loops times 1 times 10 to the minus 23 amp meters squared. Mu is equal to 6.063 amp meters squared. And this is about twice what we had calculated in the previous example. Now, we were right in the previous example. The error comes here, but it's not bad. We used big oversimplifications. I mean, we used the Bohr model, which they go in little perfect circles, but being twice off is still within the same factor, so this isn't very bad in terms of estimations. And so we did this using some pretty messy approximations, and we got within twice. And one thing to know, electrons, as far as we've seen in lab, really truly behave like point charges with 0 radius. Very, very cool. All right, so let's go look a little bit at the modern theory of magnets. So basically, you need to have all of your dipoles aligned in just a way to get a magnet. So you've probably picked up iron that doesn't act like a magnet, and that's because it has a disordered magnetic field. So the magnetic field of this piece of iron would be 0. Now, you could order it by applying something with a magnetic field to it, and then you would get these dipoles to align, and then you would get a magnetic field. So you use a magnet, or you could wrap a current carrying wire around it, and the magnetic field of those coils could magnetize it. And if you do, so wrap a wire around iron, and you have an electromagnet. All right.